Okay, alright, welcome back everybody. So, yesterday I ended with a quick review of some facts. So these are mostly algebra facts about roots of polynomials. This will be very important to us, not just immediately, but also for, well, pretty much for the remainder of this Chapter 2 material, which is higher order equations, because as we'll see, understanding the solution to homogeneous equations of this type is going to rely on being able to find and characterize all the roots of its characteristic polynomial. So it really reduces, what's a differential equations question to something that's entirely algebraic, because it turns it into finding roots of polynomial, right? Which is the beginnings of algebra. So, alright, so our quick algebra review. As I said, a degree n polynomial has exactly n roots. That's counting with multiplicity. So for instance, if I have the polynomial, it's just x squared, right? So f of x is equal to x squared. That's a quadratic polynomial. It has two roots in this sense, 0 and 0, right? So you might say, wait, that only has one root. But that one root is a double root, okay? And so it's counted twice. All right, and of course it doesn't have two distinct roots. It has one real double root. Okay, so that's how this counting works. If you have a polynomial with real coefficients, then if that polynomial has complex roots, all of those must occur in conjugate pairs. So you can't have like a single complex root, say mu plus I nu, without also having its conjugate as a root, which is mu minus I nu. So that's another important fact that's going to allow us to vastly simplify what kind of, well, decently simplify what kind of things can happen here. And number 3, suppose I have fully factored this polynomial. So here we go. There it is. Fully factored into its linear factors, right? And we haven't, like I said, I'm going to ignore that, there's some restrictions placed around the fact that these have to occur in conjugate pairs. So like when I do this, I actually know a little bit more in this situation, but forget that for a second. Say that you either have this thing fully factored, or I just give you a list of the roots, right? So if I give you a list of the roots exhaustively, then I'm going to list them with multiplicity. So in the list, right, a root that has multiplicity greater than 1 would be listed multiple times, okay? But anyway, let's say I give it to you in fully factored form so that you can read off the roots. Then a couple of things. So if I've done this in such a way that I gave you an example here where I had listed this fully factored, but actually there was more efficiency here, where I could combine this z minus 2 factor with the z minus 2 cubed factor over here to be a z minus 2 to the 4th factor. So suppose that I've done all those simplifications already, so that all these z sub i's, right, are different. Okay. Then this power on the factor corresponding to that root is the multiplicity. That's how we define the multiplicity of z sub I. So if it has multiplicity 1, we call it a simple root, or we'll say it has multiplicity 1. If it has multiplicity 2, we'll call it a double root, or just say that it has multiplicity 2. For higher roots, we typically just say, oh, it's a root of multiplicity 3, 5, 7, whatever. Okay. All right. So this is just a quick review of those things. All right. Now, how does that kind of lead into where I'm going to next, right? So, as we've already seen, here's another fact. An nth order differential equation. Of course, this is nth order linear constant coefficient homogeneous equation has a characteristic polynomial with degree n. Well, I mean, just from the definition of the characteristic polynomial, this is easy to see, right? So if I start out with an nth order differential equation like this, what that looks like is the following. A1y prime plus a not y is equal to 0. What is the corresponding characteristic polynomial? Well, that's easy to write out. It's just z to the n plus a sub n minus 1 z to the n minus 1, and so on. Right? Plus a1z plus a naught. Right? So this characteristic polynomial goes with this differential equation. So easy to see that the order of the differential equation is the degree of the characteristic polynomial. Returning to this first fact, since the degree of since a polynomial of degree n has exactly n roots counting with multiplicity, that means that for an nth order differential equation, there are exactly n roots to this characteristic polynomial. Thus, counting with multiplicity, P of z has exactly n roots. These n roots correspond to n linearly independent solutions to my differential equation star. All right. So, if we go back to our definition of Wronskian, technically we defined the Wronskian to be a thing that we could compute for n solutions to a differential equation. We didn't do any of those by hand. We only computed the Wronskian when it was a second order equation, so that just had us taking the determinant of a 2 by 2. And typically in this course, you're not going to have to take the Wronskian of anything bigger than a 2 by 2. But this is just to know that it could actually be done. So the Wronskian can be defined. It, in fact, is defined generally for n solutions, which would require you to take the Wronskian, or take the determinant of an n by n matrix. Okay. All right. So these correspond to, but let's say that, let's say I've already done that check. Okay, it turns out I'm not going to have to do that check because if I listen to this boxed thing, they're automatically guaranteed to be linearly independent. Okay, and thus, so call these solutions y1, y2, all the way up to yn. Thus, a general solution to star is given by y of t is equal to c1 y1 of t plus c2 y2 of t, and so on, all the way out to cn yn of t, where the ci's are just arbitrary constants. Right? And these y1, y2s are the solutions, the n linearly independent solutions that arise from the roots of the characteristic polynomial. Okay. Now, we've already seen this in some form. I've already mentioned that this is exactly how this works. Okay, but this is saying, more explicitly that, well, if my goal is to find general solution to this thing, star, right, then that is achieved by first finding the roots and the multiplicities of each root of the characteristic polynomial, P of z. Okay. Then I need to understand the process that allows me to assign these solutions to those roots. All right. So let's see how that works. So the process for finding a general solution of star. What is the process? Well, let me bring back star so you can remember what it looks like. So it's this equation. So step 1, write out its characteristic polynomial. P of z. Find all of its roots and their multiplicities. Second, assign to each root some number of solutions by a process we'll see soon. Notice I say some number. Okay, so assign to each root some number of solutions by a process we'll see soon. It turns out the some number here is equal to the multiplicity of the root in question. So, for instance, to a simple root, to a root of multiplicity 1, I'm going to be assigning a single solution. Okay. To a root of multiplicity 2, I'm going to be assigning 2 solutions that are linearly independent. And for higher and higher multiplicity roots, I'm going to be assigning more and more solutions. So a root of multiplicity 5 will have 5 solutions associated with it. A root of multiplicity 1 will have 1 solution associated with it. So the total number of linearly independent solutions in part 2 is n. Well, now we know why it's n, right? Because you have characteristic polynomial. This is an nth order equation, right? So this star is an nth order equation. The characteristic polynomial then is degree n. If I'm assigning to each root some number of solutions equal to its multiplicity, remember our fact about multiplicity is if you took the multiplicity of every single root and added them up, you have to get n. Why? Because if I fully factored a degree n polynomial, right? I fully factored a degree n polynomial into these factors, then if I were to multiply all of this out, the highest power of z showing up has to be n. But the highest power of z is the sum of all these m's. So it has to be n. So the sum of all the multiplicities is n. So the total number of linear solutions in 2 is n, and thus a general solution of star is the thing I wrote at the bottom of the last page. So y of t is c1 y1 of t, and so on all the way out to c2 or cn yn of t. Right, so you have n of them at the end of the day, regardless of how you've labeled those, right? Then you get n of them, and so you write a linear combination of those in linearly independent solutions. It turns out this is the general solution. So this is it. Okay. Now, to say a couple of things. 1, 3 is kind of an automatic step, right? Because if I found all n of these from 2, 3 is just saying write it out like this, right? And that's the general solution. So 3 is not really much work on my part. So then all the work is happening before this, all right? Write out the characteristic polynomial, that's easy. Find all of its roots and their multiplicities. Now, if you were trying to do this by hand and I give you a degree 10 polynomial, right? That could be pretty rough if I don't give you any hints as to what those roots are, or I don't give it to you in some fully factored or at least partially factored form. This might be a little bit confusing. Okay, this could be hard. But I'm not going to do that, right? This is not me forcing you to try to factor degree 10 polynomials. That's not really the point of the course. So typically, this will be given to you in a form that makes finding the roots and their multiplicities very easy. So we'll go over an example later that's kind of typical or very representative of the sorts of problems that you could be asked to consider. Number 2, so here's where really all the magic happens. So number 2, assign to each root some number of solutions by process we'll see soon. This process is really the key part, right? One is going to be something that's more akin to bookkeeping because you're basically going to be given the roots in some form. 3 is once you've got all these solutions assigned to each roots and you've assigned enough of them, then you just form this linear combination. So that's pretty straightforward. So this process that I'm talking about is really the meat of what's going on. All right. So how does this work? All right. Well, let's see here. So this, give me 1 second. I have to do something really quickly. I'm going to put the music back on for a second, and I'll probably just clip this out when I post the video. So give me just a second while I do this. I have to make sure the house doesn't collapse. So be right back in like 3 minutes. Okay, sorry about that. The cats were somewhat destroying the house, so I had to pause for a second to fix that and make sure they didn't completely destroy the house. So anyway, okay, so how does this process work? Well, maybe let's see the easiest thing. So let's say P of z has a simple real root. We'll call it R1. Okay. Then we assign to R1 the solution e to the R1t. Well, we've already seen this. We've already seen how this works in the case of a second order equation. This is exactly the thing we did. So to a simple real root, to a real root of multiplicity 1, we just assigned e to the R1 of t as our solution. So you can check that this will be equal, or this will be a solution to that differential equation. If R1 is a root of the characteristic polynomial, this is definitely going to be a solution. All right. Let's say P of z has a simple complex root. Or I should say a simple complex pair of roots. What do I mean simple? Well, a complex root could have multiplicity higher than 1. If you want to see how that works, let's do a quick aside. So on quick aside here, let's let P of z be equal to z minus 1 cubed times z plus 2 times z plus 5 squared times z squared plus 1 times z squared plus 9 squared, and maybe times z plus 2 here. Okay. Well, I've done something that I typically won't do here. Clearly, you notice that I've done something stupid here, and I have z plus 2 to z plus 2 here. That's not what I consider fully factored. So I would want to combine these two into this. So let's get rid of this factor and rewrite this in a proper way. There we go. So first of all, what are the roots? Okay, so the roots are z is equal to, from this term, I get the root 1, but it's a root of multiplicity 3, so it gets listed 3 times. Okay. What's the roots of this? Well, so from this one I get minus 2, but it's a root of multiplicity 2, so it gets listed twice. Similarly, minus 5 is a root of multiplicity 2, so it gets listed twice. This last term, or sorry, these last two terms, you notice that these are not linear factors. These are quadratic factors, right? Well, this is exactly what I mean by this is not always something that is going to be fully factored, right, over, we'll say, the reals, right? What that means is that z squared plus 1, I can't factor that unless you're allowing me to write out polynomials that have complex coefficients. Okay, so if I'm not being allowed to do that, then I can't factor these anymore. But what can I do here? I could say, well, the roots of z squared plus 1 are plus or minus I. All right. And those occur each once because these are both roots of multiplicity 1. You can think of having factored this as z minus I, z plus I, if you like. All right. In which case, both of these show up once. For this thing, z squared plus 9 squared, I get plus or minus 3i and plus or minus 3i again. Why? because these things are, each of these complex roots that I get here, the pair, each of them in the pair have multiplicity 2. Okay, the way you can think about it is if I were to factor this out, right, this would factor as z minus 3i, z plus 3i, but because of this square term, it would factor as z minus 3i squared, z plus 3i squared. So both 3i and minus 3i have multiplicity 2, so I would get 2 of these. Now, this also gives me a quick way, without counting the powers here, although it's the same thing, counting these powers and counting the number of roots, if I've listed them exhaustively, gets me the same thing. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, so what is the degree of the characteristic polynomial here? It's 13, right? Which means this is the order of the differential equation in question. So if I were to ask you what is the order of a differential equation that has this as its characteristic polynomial, you'd say it has to be order 13. This is an order 13 differential equation. So the highest derivative showing up here is a 13th derivative. Okay, so this is a pretty high order equation. All right. Okay, so this is how writing these things out in multiplicity works. This is how identifying the multiplicity works. So let's go back to my process. Okay, so say P of z has a simple complex pair of roots. So we'll say that this complex pair of roots is mu plus or minus I nu, right? So both of those have to be roots of the characteristic polynomial. Then 2 mu plus or minus I nu gets assigned two solutions. Okay, the first one is e to the mu t cosine nu t. The second one is e to the mu t sine of nu t. Hey, this looks familiar. This is exactly what we wrote out for our homogeneous equation, right? So in this case, this would be our y1 of t, and this would be our y2 of t. So if P of z has a simple complex pair of roots, then to that simple pair gets assigned two solutions, y1 and y2. Okay. All right. Now, the real question, say P of z has a simple root, or sorry, has a root that is real with multiplicity m. So we'll say z is equal to r, and the multiplicity of r is equal to m. Okay. Then I associate m solutions with this root, with z equals r. What are those m solutions? They are as follows: e to the rt, t e to the rt, t squared e to the rt, t cubed e to the rt, and so on, all the way up to t to the m minus 1 e to the rt. So this would be y sub 1, this would be y sub 2, this y sub 3, this y sub 4, and so on, all the way up to y sub m. Okay. All right. So this is how I would do this for a root that is real and has multiplicity m. Compare this to the case of a double root for a second order equation, right? So for a second order equation, the highest multiplicity of a real root could be is 2, right? Well, the highest multiplicity that any root could be is 2. And so the largest multiplicity we're going to deal with is 2, which means that we could only ever see 2 such solutions assigned in this way. But here we're going to get m of these. Okay? So this is how this works. Now you see where the e to the RT and t e to the RT comes from in the order 2 case. All right, what about the next step? Say P of z has a complex pair of roots. With multiplicity m. So we'll call our complex pair of roots mu plus or minus I nu. We'll say their multiplicity is m. Okay. Then remember, each complex pair, right? A complex pair is technically 2 different roots. So this would be really 2 roots of multiplicity m, which is going to give me 2m total, if I'm following this pattern, solutions that I should assign here. So to a root z equals mu plus or minus I nu of multiplicity m, we assign 2m solutions as follows. So I have e to the mu t cosine nu t, e to the mu t sine nu t. This is the 0th term. Then I have t e to the mu t cosine nu t, and t e to the mu t sine nu t. Next would be t squared e to the mu t cosine nu t, and t squared e to the mu t sine nu t. And then I keep going all the way up to t to the m minus 1 e to the mu t cosine nu t, t to the m minus 1 e to the mu t sine nu t. So that's 2m. I'm not going to try to label these like y1, y2, y3, y4. I'm not going to try to label them like that. The point is that here's my, I get 2 here. That's the first order thing, or the 0th order. This is first, and so on, all the way up to m minus 1. So this is a total of 2m, right? Total of 2m solutions. All right. So this covers all bases. Notice that I could have actually stated parts 3 and 4. I could have stated both of these at first and just said, hey, of course this applies if the multiplicity is 1. Right? So if m is equal to 1, notice what both of these give you. If m is equal to 1, all I would get is this first one, e to the RT. That's case 1. And if m is equal to 1 in this case, all I would get is these first 2, which is exactly what I said for number 2. So technically, all you need here is steps 3 and 4, knowing that this applies when the multiplicity is also equal to just 1. Okay, but this is exactly the process. Okay, so let's see how this process works on an example. Okay, so what is my example? Well, let me do another one. So example. Suppose P of z is the characteristic polynomial of some linear constant coefficient homogeneous differential equation. Okay. And let's say that P of z is equal to z plus 1 times z minus 2 squared times z squared plus, we'll say z squared plus 4 times z minus 5 cubed times z squared plus 9 squared. Okay, so two questions. One, what is the order of the differential equation? And two, find the general solution to the differential equation. Okay. So two things I'm being asked to do here. All right. So suppose P of z is a characteristic polynomial for such a differential equation. There it is. I fully factored it. And I want to know what is the order and what's the general solution. So the order I could immediately find by just computing the degree of this thing. So degree of this thing is going to be, well, 1 plus 2 plus 2 plus 3 plus 4. All right. Well, let's just make sure that when I list out these roots, I've listed out all of them and exactly the multiplicity they have so that I can more easily count this to see that that makes sense. But let's see. This is 1 plus 2 is 3, plus 2 is 5, plus 3 is 8, plus 4 is 12, so this should be order 12. Okay. All right, so this should be order 12. We'll see that we actually get 12 roots when we list this out. So what are the roots? And what are their multiplicities? So z is equal to minus 1 is a root coming from the first factor. Multiplicity 1, because the power here is 1. So it's minus 1. The next root is 2. It's a double root, so I list it twice. Okay. The next root is plus or minus 2i. Okay. So these are both simple roots in this conjugate pair, right? Because the power here is 1. Next, I have 5, and that's a triple root, right? That's a root of multiplicity 3. So there it is. And lastly, I have plus or minus 3i. And each of those is a double root. So there we go. Let's count and make sure that this is actually equal to 12 so that we've got them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes. Okay. So there's our roots listed with multiplicity. This is an order 12 differential equation. So I expect, if I'm following my process correctly, at the end of the day I should get 12 solutions that are linearly independent. Okay, if I had to actually check that those were linearly independent, I would be computing the Wronskian for 12 solutions, which would lead to me taking the determinant of a 12 by 12 matrix. Okay, so I'm definitely not going to do that. It turns out that this process is always going to yield linearly independent solutions. So how does this assignment work? So for the root minus 1, what solution do I get? I get e to the minus t. For the root 2, which is a double root, what do I get? I get e to the 2t and t e to the 2t. Those are the two solutions I get. For the conjugate pair plus or minus 2i, what do I get? I should get two solutions, and I do. I get e to the 0t cosine of 2t, right? And the second one is e to the 0t sine of 2t. So I get cosine 2t sine of 2t there. All right. What about my triple root 5? I should get three solutions. So I get e to the 5t, t e to the 5t, and t squared e to the 5t. And then lastly, for my multiplicity 2 conjugate pair of roots, plus or minus 3i, right, but they each have multiplicity 2. What do I get? I get cosine of 3t, again, because the real part is 0 here, so it's e to the 0t cosine of 3t, e to the 0t sine of 3t. But also, I get t e to the 0t cosine 3t, and t e to the 0t sine 3t. That's all of my pieces. And so, my general solution to the differential equation is y of t is equal to c1 e to the minus t plus c2 e to the 2t plus c3 t e to the 2t plus c4 cosine of 2t plus c5 sine of 2t plus c6 e to the 5t plus c7 t e to the 5t plus c8 t squared e to the 5t plus c9 cosine 3t plus c10 sine of 3t plus c11 t cosine of 3t plus c12 t sine of 3t. That is my general solution to that degree 13 equation, or that order 13 equation. Now, what this means is that for an order 13 equation that has p as its characteristic polynomial, right, so it has those roots as the roots of its characteristic polynomial, the most general form a solution could take to such a thing is this. Okay, that has 12 terms. So this is parameterized by 12 arbitrary constants. Again, notice that this keeps up with the pattern of you have an order n linear differential equation. The general solution is parameterized by n arbitrary constants. So in the first order case, we had parameterization with a single arbitrary constant. Second order case, two arbitrary constants, c1, c2. In the nth order case, this is n arbitrary constants in this fashion. Okay, so that's how this works, and these sorts of questions are things that I definitely like to ask conceptually, right? This is, for a lot of second order stuff, this is as conceptual as it gets to construct these solutions, because here, notice that I'm not really doing any solving. I'm just kind of following this process and writing down these prescribed solutions given the root and multiplicity of the root. Okay. So we very much reduced solving these linear homogeneous differential equations to an algebra question, that is finding roots of a polynomial. Okay. Now, that sets us up for the big topic, which is really the meat of the course. All right, so the meat of the course. What is this? Linear constant coefficient. Inhomogeneous or non-homogeneous. Now, I can keep up this process by keeping it maximally general. I can write this, everything I do here on, I could write out as an nth order equation. But because when you're actually computing with this stuff, everything is going to be second order just to make the computations a lot less tedious, I'm typically going to write this. Okay. Maybe, of course, it's an IVP, so you have, this sort of thing too. Okay, but regardless, this is the equation we're studying. Again, I could have written this as a generic nth order non-homogeneous equation, and everything I'm going to say here carries through. I could still ask you questions about non-homogeneous nth order equations, but just to make this simpler to write, I'm going to be referring to second order equations, but I'm not losing any generality here. Okay, so question is how, right? The question, how can I use my knowledge of solving homogeneous equations to solve these inhomogeneous equations? That's the big question here. Now, so the solution to the homogeneous thing is itself a crucial part of what's going to be the general solution to this thing. All right, but but we'll see that that part is, because of this process we've set up for the homogeneous equations, that part is kind of automatic. That's going to definitely be the easy part of what's going on. And 95% of the effort in any of these problems is going to rely on doing something else. Okay. So the answer is first we define the associated homogeneous problem. So the associated homogeneous equation of, we'll call this asterisk or star. So what is the associated homogeneous equation of this? The associated homogeneous equation would be this thing. So you just take this equation and you replace the right-hand side function with 0 instead. This is called the associated homogeneous equation for this differential equation. So, easy answer is, I take the differential equation that has the right-hand side function that is bad, that I don't like, and I just zero it out. I just say, let me say that that's actually 0. Right? You miswrote something. You didn't mean to put t squared on the right-hand side. You meant to put 0 on the right-hand side. So this is the associated homogeneous equation. Now, the general solution to this, so the general solution to this is written as y sub h of t. This is the homogeneous solution. The homogeneous part. Okay. Now, here is a quick aside that lets me shortcut writing out these things even more. So here's a quick aside. Let's say we have the differential equation looks like this. So we'll say it looks like this. So it's still constant coefficient, but it's an nth order equation. We can say let L be this differential operator, which is a thing I talked about on either the, I think I might have talked about it on the very first day of class. So if you go all the way back to lecture 1, if it's not lecture 1, it'd be in lecture 2. But if you go, all the way back to either lecture 1 or lecture 2, you'll see me writing out a differential operator. Here, my differential operator is going to be d to the n. That is, d is the derivative operator. So, right, d is d dt. That's what that is. So taking the nth order derivative is taking the nth order derivative in this sense, plus a sub n minus 1 d to the n minus 1, and so on, all the way out to a1d plus a naught. So let L be this thing. Then this equation can be rewritten in a much more compact form. Ly is equal to f of t. Okay, it's you take the operator L, apply it to y, that's equal to f of t. Let's see what it means to apply it to y. So think about this as being a kind of polynomial. In fact, now that I've written it like this, you probably notice something, right? You probably notice something. What is another way of defining the characteristic polynomial? Note, L is equal to the characteristic polynomial with d plugged in. So this expression is just like I took the characteristic polynomial for this thing. Of course, I know that the characteristic polynomial, technically, I'm defining it for a homogeneous equation. We'll see, though, that the characteristic polynomial for the associated homogeneous equation, that is exactly this L, right, with z plugged in instead of d. Okay. So L is just the characteristic polynomial with this d operator evaluated at each z. Okay. So anyway, so then d to the n times y, that's really the nth derivative of y. A sub n minus 1 times d to the n minus 1, that's a sub n minus 1, the constant, times the n minus first derivative of y, that's exactly this, and so on, down to every single term, down to a naught times y. Right? And that's all on the left-hand side, is equal to f of t. So this is a very, very nice way of writing out this equation so that my hand doesn't die, and so that I can talk about these things quickly. Okay. All right. So what do I do here with this? So the idea here is that now the associated homogeneous equation for this to Ly is equal to f of t is just Ly is equal to 0. Okay. That's a very simple way of writing out what we mean by the associated homogeneous equation. Okay. Now, what can I say about a general solution to Ly is equal to f of t? So I want a general solution to Ly is equal to f of t, which you can remember, this is the same as this, is the same in the n equals 2 case as this. So this is the thing I'm trying to find a general solution for. How do I do this? Well, firstly, I write out the associated homogeneous equation. Ly equals 0. Find its characteristic polynomial, p of z, roots, which leads to find general solution, y sub h of t. Now, this is a general solution to the associated homogeneous equation. So this is y sub h of t. That is solving a homogeneous equation. That's what we've been doing for the last 2 days, right? So that's something we can actually quickly do. We can actually quickly write out. Okay. So that's not too bad. All right. Secondly, my next step, I want to find a particular solution. Y sub p of t to Ly is equal to f of t. What do I mean by particular solution? Well, I want to find just any old solution to Ly is equal to f of t. Now, wait, you might say, isn't this circular, right? Because you started out saying you wanted to find a general solution to Ly is equal to f of t, but then your second step in the process is finding a solution to Ly is equal to f of t. So how's that not circular? Well, I want to find a general solution to Ly is equal to f of t, meaning I want to find the solution, the most general form that any solution to this thing has to take, right? But that's not what I'm finding in step 2. In step 2, I'm just finding any solution that works. Okay, so I'm not saying it's going to be the most general form that a solution could take. It's just going to be some solution that works. And that's the reason for calling it a particular solution. It's just some solution. All right, so this is just any solution that works. Now that might sound like we're not putting a lot of restrictions on this, but I assure you, this is the hardest part of this process. So finding the particular solution is where 95% of the work in this process goes. Okay. Once I have found this particular solution, the general solution to Ly is equal to f of t is y of t, which is the homogeneous solution, y sub h of t, plus the particular solution. And there it is. Okay, there it is. Now, why can I say this? Why can I say this step 3? This is really a linear algebra fact. So this is equivalent to the statement that when you have a homogeneous matrix equation versus a non-homogeneous one, so let's do another little aside here. When you have a matrix equation that maybe looks like this, ax equals b, all right, how is a solution to this related to a solution to the associated homogeneous matrix equation ax equals 0? Well, if this thing has a solution, maybe I'll call this x sub h, and this thing has a particular solution x sub p, so let's say that a xp is equal to b, then the general solution to ax equals b is x is equal to the homogeneous solution plus the particular solution. It likely wasn't written out like this to you in your Math 240 course if you've had 240, but this is what was going on. Of course, maybe this only has a single solution, right? And in that case, the general solution is unique. If this only has a single solution, then we know that A is invertible, so the columns of A are linearly independent. So here, right, I know that this has only the trivial solution. So this x sub h is actually the 0 vector here, and this particular solution is the unique solution. But, of course, I also know that in the event that this has infinitely many solutions, all right, which is always possible, then this homogeneous thing is typically characterized by one or more free variables, right? So this thing is there's going to be infinitely many of these solutions. So this is going to be some general solution written in like parametrized vector form or something here. And so this general solution is really going to describe the form that any solution has to take. The way of going forward to check this is actually pretty easy. We'll do that in differential equations land, right? So we can quickly check what is L of y sub h plus y sub p. Well, this is because L is linear, this is L of y sub h plus L of y sub p. But y sub h is the general solution to the homogeneous equation. So L of y sub h is 0. And L of y sub p, well, y sub p is a particular solution to Ly is equal to f of t. So L of y sub p is equal to f of t. So this right-hand side is equal to f of t. So L of y sub h plus y sub p is equal to f of t. So y sub h plus y sub p solves Ly is equal to f. Okay. So this is like one direction. To show the other direction, I'm not going to get into that too much, but it really is analogous to that linear algebra example I gave you with matrix equations. Okay. So let's go back to this. Page. This is the entire process. Here's my general solution. So I need the homogeneous solution, which we've spent the last couple days figuring out how to do. And I need the particular solution, which we're going to spend several days talking about how to find. And once I have both of those, I sum them up, and that is the general solution. So how much effort is required in each part? This is like 5% effort. This is like 1% effort. All right, so this is 94% of the effort goes into finding the particular solution. Now that might seem like not a particularly, pun intended, balanced way of solving or of a process to solve something, but this is just how it has to be. So finding this particular solution is by far the hardest part of these equations. Finding the associated homogeneous equation, you're going to be so used to writing these things out, you're going to be sick of it by the end of the course if you haven't already gotten that practice. So next homework will definitely give you that practice of just writing down a ton of solutions to homogeneous equations. This thing is easy, because once you have y sub p, you're just writing them out. You're literally just taking the thing you've already found in the first step, the thing you found in the second step, and just putting a plus sign between them. So that takes no effort. So then finding this particular solution is where almost all the effort is going to be. Okay. All right. And so there are going to be two main approaches to finding y sub p. So question: how do I find a particular solution, y sub p of t? The answer is we have two main methods. We are going to see other methods that allow me to answer related and maybe more general, in some cases, questions. But the two main methods for explicitly finding a particular solution are known as undetermined coefficients and key identities. That's the first. And key identities, that's the second. Now, here's the thing. You never have to use one over the other. Like, I'm never going to, tell you, like, you have to use key identities or you have to use undetermined coefficients. You will get a choice. So you will always have a choice here. I'm going to teach both of them. Okay, so we will spend plenty of time developing everything that needs to be developed to make all this work. Okay, and in either case, right, you will be able to construct a particular solution. You will always have a choice in which of these you use. Okay, undetermined coefficients can sometimes be seen to be a little bit more intuitive. Typically, it's taught as if you're finding this by guessing the form the solution has to take. Of course, you're not really guessing, because you can show mathematically that there's really only one form that it can take. So, in fact, you're using the fact that all of this is determined to find these undetermined coefficients. So that's really what's going on there. But students a lot of times like it just because it has a feeling of it's a little bit more intuitive or easier to get a grasp on. The key identity stuff requires, it's a little more abstract and less intuitive. But in a lot of ways, if you actually understand what's going on in the key identities case, it's actually simpler than undetermined coefficients. Undetermined coefficients can lead to some computations that are pretty obnoxious and pretty nasty, that key identities makes really, really simple. You can do in like 1 or 2 lines. But it does have the downside of, like I said, being maybe a little bit hard to get into, because it's going to rely on you doing some algebra and some considerations that you've really never done before in any other class. But that being said, there is no difference in their power in terms of what problems they can solve. They both apply to the exact same types of problems. There's never going to be a problem that you can't do with undetermined coefficients that you can do with key identities, and vice versa. Okay. So that's the main point. All right. Okay. Well, I think that the best thing to do now is to, in preparation for this, in preparation for both of these, I have the following. So before I can even start the process of doing either of these, okay, I have to be careful here, and I have to define all of the quantities that are needed to even get the process rolling. Okay, so what is that? Well, first of all, what sort of equations are these going to be applied to? So we will only apply these methods. So that's undetermined coefficients, key identities, to problems Ly is equal to f of t. And like I said, maybe I have some initial conditions. Y of t sub I is y naught, and y of t sub I is y1. We'll only apply these methods to problems like this, where f of t is in characteristic form. So, first thing is we have a little bit of rain on our parade here because we're not going to be able to do these in general when the right-hand side function is completely just a general function. Okay, so if f of t is like the natural log of t, for instance, we're actually not going to be able to use either of these. If f of t is like 1 over t, we're not going to be able to use either of these. So that might, raise some red flags. You might say, wait, if we can't do it even for something like that, which maybe you don't find either of those particularly exotic functions, then, what kind of things can we even apply it to? So the idea is I want to look at the right-hand side and say, I want to restrict my attention to functions that basically are of a form that when you take their derivative, you get something else in that same form, right? So, for instance, the natural log is not, it doesn't fit that bill, because when you take the derivative of the natural log of t, you get 1 over t, right? So you go from a log thing to like 1 over t, and I don't really consider those to be the same sort of thing, all right? Versus if I take the derivative of an exponential function, well, I know what happens, right? I get another exponential function, right? So taking derivative of like an exponential thing, I get another exponential thing. Taking a derivative of a polynomial, I get a polynomial. Taking a derivative of sine or cosine leads me to sine or cosine, right? So what if I restrict my attentions? So since I know things like the product rule, right? I know that products of those things, and I know that derivatives are linear, so they split up across sums. So products and sums of those things are nice, and they fit this bill of they are the same. When I take their derivative, they're the same type of object. So what does it mean for f to be in characteristic form? Okay, so we say f of t is in characteristic form if, let me get some paper underneath this paper because this isn't writing as well now. So we say f of t is in characteristic form if f of t is equal to, we'll call it like alpha sub d t to the d plus alpha sub d minus 1 t to the d minus 1, and so on, all the way down to alpha 1 t plus alpha naught, okay, times e to the mu t cosine of nu t plus beta sub d of t to the d plus beta sub d minus 1 t to the d minus 1, and so on, all the way out to beta sub 1 t plus beta naught times e to the mu t sine of nu t for d some natural number and mu and nu some real numbers. So before I go on and label some things here, I want to draw your attention to a couple of things. One, what is this first term? It's a polynomial times e to the mu t times cosine of nu t. The second term is polynomial times e to the mu t sine of nu t. So really this is polynomial times exponential times cosine plus polynomial times exponential times sine. Okay. Now, the point is that these alpha sub d's and beta sub d's, they could be 0, reducing the degree here. So the degree of this polynomial, right, if alpha sub d is non-zero, is d. If beta sub d is non-zero, this also has degree d. But the point is that it doesn't have degree larger than d, right? And like I said, maybe all these betas are 0, okay? We're going to see plenty of examples of this because identifying whether a function is in characteristic form is extremely important. Okay, this is the beginning of the process, and if you can't do this, you can't even get started on solving these equations. So I wanted to define 3 quantities: the degree of f. Notice this is different than polynomial degree because f is not itself a polynomial. It's just this weird thing here, right? The degree of f of t is d. This number, right? This degree of the polynomial showing up here. The other quantity I want to define is the characteristic of f of t is mu plus I nu. That's what we're going to write, where mu and nu are showing up here. Okay. This is extremely important. This is not just something that you can brush off at all. This is required for even like the beginning step of the process. I can't stress enough that you cannot even begin the process of either undetermined coefficients or key identities without having written explicitly the degree of this thing, the characteristic of this thing, and we're going to see one more quantity called the multiplicity of this thing. But I'll define that next time. So we will start doing these on Monday, so this is a pretty good chance for a break. I'm going to assign another homework tonight that's going to be quick and dirty. It's just going to be having you do homogeneous problems, and it will be due Monday, since you've seen enough to do that now. So that homework will be due Monday. And then on Monday we will start doing undetermined coefficient stuff. Okay, and then your first exam will be given to you next week. So next week, I believe I said the 16th or 17th is about when I would assign it. You'll have 24 hours to do it. So so be looking for that. I will have another office hours session next week, so I'll let you know when that's gonna be. So pay attention to Elm's announcements. Other than that, I will see you all on Monday, and have a good weekend.